Our next speaker is Professor Zoryana Novosad from Lvov University of Trade and Economics. And yes, so you may proceed.
Thank you very much. The theme of my talk, the conditions of hypercyclicity of weighted backward shifts. I will start from classical results about hypercycle, topological transitive, and mixing operators. Let X be a Fresh linear space. An operator T from X to X is called hypercycle if there is a vector X from X. Those orbit this set is dense in X. Every such vector X is called hypercycle for T. The study of hypercyclicity started from Birgov's results in 1929. This result asserts that any operator TA of composition with translation is hypercycle in a space of entire functions on the complex plane C. The Birkov's translation TA has also regarded as a differentiation operator. Also, MacLean in 1952 showed that differentiation operator is hypercycle too. Also, Rulevich operator, the unilateral backward shift, is also hypercycle. And in 1991, Godefroy and Shapiro generalized this Birgov's result to the space entire function on Cn. And also they get coefficient C alpha. Birkov coefficient is a power n and n factorial, but they have a generalized coefficient C alpha. It is known that only translation operator TA is hypercycle on composition operator on entire functions on a complex plane. It is known there is no hypercycle linear operator on any finite dimensional space. We have the next question. Does an infinite dimensional space support a hypercycle operator? We have to answer the results of Ansari in 1997 and Luis Bernal Gonzalez in 1999 that every infinite dimensional separable Banach space supports a hypercycle operator. Now, we have two definitions of a topological transitive operator and a topological mixing operator. Let X be Banach space. A continuous operator T from X to X is called topological transitive if we have for each pair U and V of non-empty objects or open subsets of X, there is some n natural number. This intersection is not empty. Also, similar definition for topological mixing operator, but we have that there exists a positive integer k. This intersection is not empty for every n is greater than k. We have next implication. Also, when operator is hypercycle, is automatically is topological transitive and topological mixing. if the underlying space is a separable Baire space, the transitivity is equivalent to hypercyclicity. Three classical hypercycle operators, Burgos, MacLane, and Shulev's operators are mixing because they are hypercycle operators. Burgos' result is important in the theory of chaos. In particular, a dynamical system T from X to X is chaotic if it has a sensitive dependence of initial conditions, and T is a topological transitive, and T has a dense set of periodic points. Now I want to speak about separability and non-separability. Orbit cannot be dense in a non-separable space. And non-separable spaces do not support hypercycle operator. Now we have question. Every non-separable Banach space admits a topological transitive operator. For Hilbert spaces, the latter question is true, as shown by Bermudez and Carlton in 2002. There exist several examples of Banach spaces which do not admit topological transitive operators. In this space L2 and L infinity do not support any topological transitive operator. We have a nice hypercyclicity criterion is known as Kitay-Gettner-Shapiro's theorem. Let X be a separable complete linear metric space, and T from X to X be linear or a linear and continuous operator, and these three conditions are fulfilled, then T is hypercycle. This is a sufficient condition, and it is known that there are hypercycle operators which do not satisfy the hypercyclicity criterion. This results we can see in book Bayard Matheron, Dynamics of Linear Operators. Similar to hypercyclicity criterion is a topological transitivity criterion. Let T be a bounded linear operator on complex Banach space X, not necessarily separable. And we have the similar three conditions. When these conditions are fulfilled, then T is a topological transitive. The existence of an element with a dense orbit implies that X must be separable. But when we have topological transitive operators, is not necessarily that X must be separable. We have two classical examples of hypercycle and topological transitive operators. According to the classical theorem of Rulevich, we have classical weighted backward shift on L2. This shift is hypercycle on L2 and on LP. This when this space is separable, but when we have a Hilbert space, possibly non-separable, we have this shift, the backward weighted shift, is a topological transitive on non-separable Hilbert space. This is a result of monosis in 2030. Now I want to speak about my result. Let X be infinite dimensional non-separable Banach space, which admits a Schauder decomposition to Banach space xk, and they have elements in represented as formula. And let Fk be a sequence of injected maps, and we have the following shifts of spaces under maps Fk. And we defined backward shifts operated by the next formula, similar to weighted shifts. Also, the main the main result, suppose the following assumptions hold, then the operator T is topological transitive. This operator satisfies condition of topological transitive criterion. Now I want to speak about example of the operator T. Let X be a continual direct L1 sum of spaces LP on 0, 1. And we have X X is a direct sum of LP and Schauder decomposition. And we have Fk as shifts of spaces. So by the theorem 1, we can assert that operator T is a topological transitive on X. And we have the next corollary: if a Banach space do not admit a topological transitive operator, that it cannot be represented as a countable Schauder decomposition to isomorphic Banach spaces. Okay, and now I want to speak about analytic function of unbounded type. This chapter is very different of previous chapter. I start from definition of analytic function of unbounded type. An analytic function f on Banach space is said to be a function of bounded type if it is bounded on all bounded subsets of X. And we denote this analytic function of bounded type HB of X. So elements of this set are called analytic functions of unbounded type. Also, we have Pn be a sequence of n-homogeneous polynomials on Banach space X with the norm is equal to 1 and T from X to X, a bounded linear operator satisfying this condition. We have a number n such that T of power n is equal to 0, when we can assert that function f is an analytic function of unbounded type on X. The next theorem, this theorem I used to prove the previous theorem 2. I used this results. Now I want to speak about connection backward shift with function on unbounded type. Let X be C0 or LP, and T is B1. So we have an homogeneous polynomial Pn. So we can assert this function f is function of unbounded type. If we take a weighted backward shift to b lambda when fn is equal this is defined by this formula. In this case, the radius of boundedness of f is infinity if lambda is from interval 0 and 1. The next connection when x is equal L1 and T is equal to B1, and we have homogeneous polynomial Pn. When this function f is also a function of unbounded type. This is a reference I used in to get my results, and thank you for your attention.